So what we've seen so far in this section is that a tangent line is capable of approximating the value of a function as long as you stay near the point of tangency. Well, suppose that we have a curve. We'll refer to this as y is equal to f of x. And we have a starting point, which up until this point we've been referring to as a. So we'll go ahead and keep calling it a. So at the point A, we'll say that's the point associated with this. There is a tangent line here. We'll do the tangent line up here in purple. So associated with this tangent line, we can make approximations. We'll say that this tangent line represents the linearization at that point. Now suppose also that we go, make a little horizontal trip this way and get to an additional point. So first thing we need to do is define the horizontal distance between these 2 points. We're actually going to use two different notations for this. This is a change in x, so we're going to refer to it in one of two different ways, either delta x or as dx. The reason that we have two different notations for this is we're also going to have two different notations for the change in y that gets created. Reason being, there is a change in y on the actual function, and that change in y we're going to refer to as delta y. We also have a change in y associated with the tangent line. That one we're going to know as dy. Now with that in mind, dx and dy are known as differentials. Normally when we see dy and dx together, we're talking about some kind of derivative, and the slope of the linearization would be the tangent, or the slope of the tangent line at a. So with that in mind, if we were interested in finding the actual change in y on our function, that would be delta y. And according to our picture here, that would simply be this y value minus this y value, what we could call y2 minus y1. Or if we wanted to actually figure out the x values, we could say that this is f of a plus delta x minus f of a. Now as far as the differential is concerned, the approximate change in y, that would be the differential dy. Now to calculate that, we can simply go with the fact that this is a constant slope, and if you take a slope times a change in x, you can get a change in y. Now that slope would be f prime evaluated at a times whatever that change in x value is. So this is known as the differential of y. Now in the event that an a value is not specified, we can also create the following. So more generally, dy would be equal to f prime of x times dx. Where generally speaking, dx will be given to you and f of x will be given to you. It'll be up to you to actually differentiate this thing. So what we can also say is that near x equals a, dy is going to be approximately equal to delta y. And that's sort of the thing that we've been relying on this entire time, is that near a particular point, the tangent line is going to be approximately equal to the actual function. So we'll work through a couple of examples in the upcoming videos.